Lesson 2-2, Weight and Normal Force. Weight is the measure of the force of gravity. If we take our main equation, F equals ma, and remember that objects near the Earth accelerate downwards at 9.8 meters per second squared, we could change this to the weight, or force of gravity, equals mg. So our weight is calculated by mg when you're near the Earth. Because it's a force, the unit is newtons, but it depends on local gravity. If you go to another planet, so that the g changes, then the weight would also change. Mass, on the other hand, is not a force. Mass is the measure of inertia, or the amount of matter. Its unit is a kilogram, and it's constant. It doesn't depend where you are. So weight and mass are different. They're related, they're proportional, but weight is a force, mass is not. Weight depends on the local gravity, depends on the acceleration due to gravity. Mass does not. So how do we solve problems involving forces? First, identify the principles involved and draw a picture. That's pretty typical of all physics problems. List your knowns. Draw a free body diagram. For force problems, then you'd apply Newton's second law. Net force equals mass times acceleration. Solve for whatever you need, and then check your answer for reasonableness. So what is a free body diagram? Well, a free body diagram is a drawing that shows all the forces acting on the object. In this case, acceleration is not a force, so we're not going to have that. But we do have four forces going to the right that are thrust, a force going backwards called friction, a force upward called the normal force, and the force downward called the weight. So our free body diagram is just showing all those forces and how they're related to each other. So you're going to represent all these forces with vector arrows. When two objects touch, there's often a force. We call this force normal force, which is the perpendicular component of the contact force between two objects. Normal in math often means similar to perpendicular. So this normal force is always going to be perpendicular to the surface, and it arises from one object sitting on top of another object, or the lower object having to push the upper object upwards so that it doesn't crash through it. In this case, with the brick on a table, the weight is pulling the block downwards, but the table pushes up. That upwards force is the normal force. And that's from Newton's third law. So the block pushes down on the table, so the table pushes up on the block. It's the equal and opposite reaction force. And it has to be there. The normal force has to be there, or else the block would go through the table. Because if the normal force wasn't there, the only force would be the weight, and so F equals ma, it would accelerate downwards. Be careful, normal force won't always equal the weight though. You'll have to draw a free body diagram, add up the forces, and say F equals ma. A 30-kilogram box of books is sitting on the floor. A 20-kilogram child is sitting on the box. What is the normal force between the child and the box? Well, we really only care about the child on the box. And so we have the child's weight pulling down, and the normal force of the box on the child pushing up. So if I go F equals ma, I have the normal force up and the weight down. Weight is calculated with mg, and we have zero acceleration. The child's just sitting there. They're not accelerating upwards, they're not flying up, they're not falling through the box, so the acceleration is zero. So my normal force would equal mg. All right, now whose mass? Well, it's just the weight of the child, so it's the child's mass. Which would give us 196 newtons. So the kid's weight is pulling down on the box with 196 newtons, and so the box is pushing back upwards on the child at 196 newtons. Well, what is the normal force between the box and the floor? So now we're worried about here. Well, forces, we have our weight going down, and that would be the combined weight of the child and the box, and the floor is pushing up with its normal force. So again, if I go F equals ma, normal force is up, the weight is down, weight is mg. Now again, there's no acceleration. This box and kid are not falling through the floor, nor is the floor throwing them up. So our normal force is mg again. Now our mass this time would be the total mass. Since we're on the bottom here, it's going to be the total combined mass. So that would be the 30 kilograms from the box plus the 20 kilograms from the child. So that'll be 50 kilograms times 9.8, or 490 newtons. A lady is weighing some bananas in a grocery store and the floor collapses. The banana's mass is 2 kilograms and the floor is accelerating at negative 2.25 meters per second squared. What is the apparent weight, or the normal force? Whenever you have a problem asking for apparent weight, they are looking for the normal force. That is what you feel as weight, is the normal force. You feel it's just the force of the contact. Well, we have our bananas. We've got the weight pulling our bananas down. And we have the normal force because they're sitting in a little scale, just pushing them back up. So if I go F equals ma, I have the normal force up and the weight down. And of course our weight could be mg. I'm looking for the normal force. The mass of the bananas is 2 kilograms and g is 9.8. Now why don't I use a negative 9.8? Because I already have the negative there pointing that it's downwards. Our mass is 2 kilograms and we do have an acceleration. Our acceleration is negative 2.25 meters per second squared. All right, so add the 19.6 and you should get 15.1 newtons is the apparent weight of the bananas. A box is sitting at a ramp angled at 20 degrees. The box weighs 50 newtons. What is the normal force in the box? So here I have my box sitting on my ramp. The normal force is always perpendicular, but the weight is going to be pulling straight down. For problems that are slanted like this, it's easiest if I say x is along the ramp, so that would be parallel to the ramp, and the y would be perpendicular to the ramp. So So we rotate our axes slightly, which means I need to divide the weight into parallel and perpendicular components. So we could use sine and cosine. The x is opposite the 20, so that would be the weight times sine of 20 degrees. And the y is adjacent to the 20, so it would be our weight times cosine of 20 degrees. So let's go ahead and we want to find the normal force. So let's work in the y direction, which is perpendicular. And I go F equals ma. I have normal force up, and then I have the y component of the weight down. So W cosine 20 degrees. Well, weight is mg, but we have no acceleration. It's just resting on the ramp. It's not flying off up into the air. It's not crashing through the ramp, so our acceleration is 0. All right, our mass. Oh, I don't know the mass. I know the weight. Well, our weight was mg, so instead of mg, let's just put weight, which is 50 newtons. And we end up with 47 newtons for the normal force.